Let us quickly look at the two more types of linear phase systems. So, we looked at odd order, even order, odd order. Now, and we saw symmetry, even symmetry. Now, what about if you had odd symmetry? That is basically you had the negative relationship. So, type 3 linear phase. Type 3 linear phase will have the following expression: m is even and it will have odd symmetry. H of n is equal to minus h of m minus n. H of m minus n. Okay. What does the sketch look like? The sketch looks like I have a value here and a corresponding negative value here. I am going to take only 3 taps. Now, the middle tap must be the negative of itself. The only number that is the negative of itself is 0. So, the point of symmetry for a type 3 linear phase the midpoint will always be 0. Okay. So, given that, can we look at what is the expression for H E of j omega? H E of j omega will have the j term, because now we are looking at odd symmetry, and that's how the odd sequences will have a expression, will have a factor of j in their phase term. E power minus j omega m by 2, and the real part will be k equal to 1 through m by 2. Notice there is no 0 term, because 0 term will be 0. This will be ck sine omega k. You are combining E of j omega and E of minus j omega with the minus sign, so therefore you get sine terms. Okay, and what are the ck's? The ck's are 2 times h of m by 2 minus k. Okay, you look at a lot of similarities with the type 1 linear phase. Type 1 and type 3 are similar. Both of them are even order. One of them has got even symmetry, the other one has got odd symmetry. Okay, the value of k will be 1, 2 all the way to m by 2. Now, look at the expression for H E of j omega. It is a function of sine terms. Okay. So, notice that H E of j0, sine 0 is 0. So, basically this will be always equal to 0. Similarly, H E of j pi, you get either odd multiple of pi or even multiple of pi, the sine terms will be 0. This will be equal to 0. So, this particular class of transfer functions has got double constraint. Type 3 linear phase has got 0 at omega equal to 0 and at omega equal to pi. You cannot do low pass, you cannot do high pass, you can do band pass. You can do other things, but you cannot do high pass, low pass. There is a constraint that you have. And let us look at the last case where you have type 4 linear phase. M is odd, length is even. H of n is equal to minus h of m minus n. This is what it looks like. Okay. First term, second term, third term, fourth term. Okay, this is what it looks like. This is type 4. It is odd symmetry. It has got odd order, even number of coefficients, so 4 coefficients. Okay, so this is type 3. Type 3. Okay, again you can write down the expression, the H E of j omega, H E of j omega. This can be written as, it will come out to be j times e power minus j omega m by 2 summation k equal to 1 through m plus 1 by 2 dk sine of, now you will get the half terms, omega k minus half. Because where is the point of symmetry? The point of symmetry is in the middle, right? This is the point of symmetry. This is the point of symmetry. So the point of symmetry is in the middle. When you factor it out, you will get expressions of this type. What is dk equal to? D subscript k is equal to 2 times h of m plus 1 by 2 minus k. Okay, and k equal to 1 through m plus 1 by 2. Okay, look at the expression for he of j omega. Notice that this will always be 0 for he of j 0. Okay, this will be equal to 0. So type 4 has got one constraint. Type 3 has got two constraints in terms of the magnitude the magnitude response, and type 1 has got no constraints. Type 2 has got one constraint. So this means low pass filter, no. High pass filter, no. This one, low pass filter, no. High pass filter, yes. Band pass filter, yes. No problem. We can do the following. Okay. So just for us to be able to remember all 4 of these, probably useful to put them together in a table. Okay, so this is going to be, the first one is the type, the condition that we have, or the expression that we have for he of j omega, any condition at omega equal to 0, any condition at omega equal to pi. Okay, so this is what we would like to capture. So let us write down type 1. The expression for this was e power minus j omega m by 2 summation k equal to 0 through m by 2 a of k. We defined what a of k was, cosine omega k. Okay, and there is no constraint. NC means no constraint. No constraint. No constraint at omega equal to 0. No constraint at omega equal to pi. A type 2 linear phase system will have e power minus j omega m by 2. Maybe it's good for us to maybe write down saying, okay, what is the value of m? Okay, in this case m was even, in this case m was odd. The symmetry, this is even symmetry, this was also even symmetry. We can capture that, and the summation will be k equal to 1 to m plus 1 divided by 2 b of k cosine omega k minus half. Okay, a constraint. No constraint at omega equal to 0. There is a constraint at omega equal to pi, that it will always be the magnitude response will be 0. Okay, type 3. Type 3 is even order, odd symmetry, and the expression that we have is e power minus j omega m by 2. Okay, summation k equal to 1 through m by 2 ck sine omega k, and this was the one that has got double constraint. It is 0 at omega equal to 0, it's 0 at omega equal to pi. I'm sorry? J. There's a j, you're right, there is a j, don't forget the j. And finally, we have odd order, odd symmetry, that will be type 4. This will also have a j term e power minus j omega m by 2 summation k equal to 1 to m plus 1 divided by 2 dk sine of omega k minus 1/2. This is one which does not have a constraint at omega equal to pi, but it has got a constraint at omega equal to 0, right? Yeah, and this has got no constraint. Okay, so in terms of applications, where can we use these particular one? Applications. Any filter. The most general form of linear phase, FIR linear phase, is type 1. So you can do low pass, high pass, band pass, anything, any filter can be designed here. Okay, here anything except high pass. Why high pass not allowed? Because omega becomes 0 at omega equal to pi. And of course, you cannot design high pass filter, no, low pass filter, no. But then you may ask, what is this useful for? Okay, it is useful for several filters, some of which I will just mention. Again, when you study the design of filters, you will appreciate it. This can be used to implement what is called a differentiator. It can be used to design something called a Hilbert transformer. So these are filters that are used in communication. So basically, there is a use for this type of this class of systems. Okay, and similarly, here again you can use the type 4 for differentiator and Hilbert transformer. You can use it for a high pass filter. Okay, but low pass filter, no, not allowed. Okay, so I hope you are able to look at this as a good canvas to understand how do we get linear phase, what are the properties that are there of linear phase, and so this will be a very useful set of results that you can keep and then you can apply. Okay. And want you to also keep in mind one more important result that comes from the study of the linear phase systems. Okay, before we move into actually designing filters, let me explain to you this particular aspect. Okay, so if you have an FIR linear phase with real coefficients, all the type 1, type 2, type 3, type 4, all were real coefficients that we were looking at. Okay, h of n is equal to plus or minus h of m minus n. Symmetry, either even symmetry or odd symmetry. This was ultimately what was there in the expression. Okay, so again, whether it was odd order, even order, does not matter. This symmetry is still the one that is present. Okay, what is h of z? H of z will be h naught, h1 z inverse dot all the way up to what you will get is h of m minus 1 and h of m. I'm going to write this as h of 1 z power minus m minus 1 using the property of symmetry, and this last one will be h of 0 z power minus m. Okay, now pull out z power minus m. What will you get? H of 0 z power m, h of 1 z power m minus 1 dot all the way. The last two terms will be h of 1 z inverse and sorry, is it z inverse? No, it will be z. And the last term will be h0. Okay, now look at the two expressions that we have. This is nothing but z power minus m h of z inverse, because what is inside the bracket is the same as what is h of z, but with z replaced by z inverse. So what we have for an FIR linear phase is a very important property which says that h of z will be equal to z power minus m h of z inverse. Okay, so this symmetry property is present. So if h of z has got a 0 at a particular location, 1 minus Z naught Z inverse. Okay, then what does the property of linear phase say? That there will be, so basically it has got many other terms, okay, but it has got this term also. H of Z inverse is basically this has to be equal to Z inverse. So there will be a term with 1 minus Z naught Z, okay, also must be there in the expression. So in other words, okay, it must also have 1 minus Z naught Z in the expression. So that when you have H of Z inverse, you will get 1 minus Z naught Z, 1 minus Z naught Z inverse. Okay, so basically we find that the reciprocal 0 must also be present when you look at the zeros of a FIR linear phase transfer function. So the statement, okay, if Z naught is a 0, Z naught is a 0 of H of Z, which is a FIR linear phase transfer function, then 1 by Z naught is also a 0, okay. Now in addition, if H of n is real valued, that means basically it's a real valued sequence. Okay, then you cannot get just a complex conjugate root. So if Z naught is a 0, then Z naught conjugate is also a 0, because only then you will get the real valued coefficients. And because it has got linear phase property, 1 by Z naught will be a 0. 1 by Z naught is a 0 and 1 by Z naught conjugate is a 0. Okay. So does this look familiar? Like a magnitude squared transfer function, right? Because that's where you have the 0, conjugate, reciprocal conjugate. All of them are present. Interesting. That's what we find in the context of a linear phase FIR transfer function. So if you have a the unit circle like this, okay, then what you have will be 4 zeros located 0, reciprocal conjugate, conjugate, reciprocal conjugate. So basically this is what it will look like. Of course, if it's on the real axis, you have the 0 and the reciprocal. Conjugate doesn't have to be there, you will get the expression. Now, if it is on the unit circle, now what you will need is a double 0. Similarly, the conjugate location will also have a double 0. If it is on the real axis, then just location and the double 0. Okay, you don't need anything more than that. That's how the zeros of a linear phase transfer function will turn out to be. So I hope this is you have a good understanding of what the linear phase property is. So linear phase relies heavily on the property of symmetry. It can be either even symmetry or odd symmetry. Depending upon the length of the filter or the order of the filter, you will get different constraints which have been captured in this particular table, and this will be helpful in terms of the designs that we can do.